Okay, so it looks like everybody's back. So welcome to the afternoon session. So for this session, we have Hayata, who's going to tell us about this big open problem, generalized quantum Stein's lemma, and second law of quantum resource theories.
Thank you for the kind introduction. I am Hayata Yamasaki from the University of Tokyo. I'm also working as a team leader in NanoQT, a startup company in Tokyo. Today, I'd like to talk about our recent theoretical results on proving generalized quantum Stein's lemma and its implication to the second law of quantum resource theories. This talk is based on joint work with Masahito Hayashi. Before going into detail, I would like to broadly talk about what I am aiming at in my research. So throughout a series of my work, I'm trying to lay a theoretical foundation that connects advances of quantum technology and our future advance of our IT society. To achieve this, I've been working on several different aspects of quantum information theory. One is how to use quantum computers. So I've been working on useful quantum algorithms, especially in the field of machine learning. And to implement useful quantum algorithms, we need how to implement it in a scalable and fault-tolerant way. So I've been working on FTQC from this perspective to bound the ultimate scaling of FTQC overheads. And also on the physical side, which is a topic of this talk, I've been working on how to quantitatively analyze and bound the efficient use of quantum resources, from which the advantage of quantum information processing arise. In all of these aspects, I've been working on several topics. One is the development of quantum algorithms that achieves exponential speed up compared to the existing classical algorithm in quantum machine learning tasks. What I'm interested in is explicit runtime bounds. And also, I would like to, in some of the other classes of works, I'm providing proof techniques to show a runtime or energy consumption advantage of quantum machine learning tasks. And to achieve, and also for the FTQC, my interest is how to reduce overhead, what we can achieve in this quantum world in the ultimate way. So I've been working on constant space overhead FTQC, both using concatenated code in 2024, and also more recently, we worked on constant time overhead, this is space overhead, constant space overhead FTQC with quantum DBC codes. And also, important subroutine called we also bound overhead on important subroutine called magic state distillation, which is also relevant to the topic of this talk, generalized quantum lemma. I'll discuss a brief connection to general quantum lemma at the end of this talk. So the main thing of this talk is generalized quantum lemma, which I will talk in the rest of this talk. If you have any questions, so I'm very happy to discuss all of these aspects during this workshop. So if you have any if you're interested, yeah, let's have a discussion on this throughout this workshop. So I start with the background of quantum science lemma. So our human society progress as our technology advances. And behind such technological advance, we always have a very strong theory that supports such technology. In 19th century, steam engines are developed, and behind that, the theory of thermodynamics emerged. At the core of thermodynamics is the second law. Second law of thermodynamics characterizes convertibility between thermodynamic states under adiabatic operations. This is fully determined by a single function called entropy, meaning that thermodynamic state x1 is converted into x2 if and only if its entropy satisfies certain inequality. In this way, second law of thermodynamics characterizes state convertibility by a single function, entropy. But now we are in the quantum era. So now we have a technology to develop quantum devices And quantum information theory emerges as a theory to support such technological advances. So quantum resource theory is a unified framework that explores advantages and limitations of quantum mechanics and quantum resources, from which the advantage of quantum information processing arise. So quantum resource theory is characterized by the choosing free operations, which is a restricted subset of operations, CPDP maps, such as for entanglement manipulation, we choose local operations and classical communication, or LOCC for short. And also relevant to the operations relevant to FTQC may be stabilizer operations, which are class operations composed of Clifford gates, state preparation, and power basis measurements. And the free states in quantum resource theory, so free states is defined as a class of states that can be obtained from any non-resourceful initial state. So it can be obtained freely from any state by free operations. And anything that is not free state is called resource state, which are non-free and potentially assist the task performed by free operations. In this framework, QRT studies manipulation and quantification of quantum resources from the operational approaches that we need as in the thermodynamics. One canonical example of quantum resource theory is the theory of entanglement. Entanglement is a resource to assist LOCC, and this serves as this is useful for various tasks, including quantum teleportation. And so in this case, the free state is the set of free states are those of separable states. These are a convex mixture of product states. Anything that is not represented in the form is called entangled. A central task in entanglement manipulation is distillation and formation. So entanglement distillation, so in order to use entanglement, we need a very particular form of entangled state called E bits, which is a maximally entangled state of 2 qubits. This is a pure state. But in the actual laboratory, what we obtain is always mixed state. So it's important to reduce noise in mixed state. So this process is called entanglement distillation. And we convert the many input mixed state into pure many copies of E bits by using free operations such as LOCC. And its optimal rate is called distillable entanglement. This is a fundamental quantity in entanglement theory. But its reverse task is equally important fundamentally and also in practice. So the reverse task is called entanglement formation or entanglement dilution. And in this case, we have many copies of A bits, and then we obtain some target mixed states, and then its asymptotic conversion rate is called entanglement cost. So this indeed equals to some entanglement measure called entanglement of formation. This is originally proved by Hayden-Hordesky-Tarha in finite dimensional case. And we recently showed that it's fully general proof, including finite dimension and infinite dimensional case. Anyway, so central goal of entanglement theory is clarify optimal protocols and fundamental limits in manipulating entanglement. To achieve this goal, various efforts have been made in the field of entanglement. A quantity of central interest is a conversion rate, asymptotic conversion rate between two mixed entangled states, which is given by the optimal rate to obtain some input state, to obtain output states per input state in asymptotic conversion under some free operations, such as LOCC. And if we recall the second law of thermodynamics, it is desirable to fully characterize such conversion rate just by a single function, let's say f of the input state and output state. And if such a second law would hold, that would mean that the distillable entanglement and entanglement cost are equal. And whether we can have such a reversible framework has been raised as an important open problem in the field. But there's a challenge because entanglement conversion is inherently irreversible. Under LOCC, we can easily see that discernible entanglement and entanglement costs are not equal in general. So we see such an example from the existence of bounded entangled state, which is an entangled state. So it's entangled in the sense that it cannot decompose into convex mixture of product states. But still, from this class of states, we cannot distill pure entangled states. So in this sense, entanglement cost and distillable entanglement are different. So one way to circumvent this problem would be considering a stronger class of operations than LOCC. One way is to convert separable operations, and we can even consider as its relaxation called PPT operations, which is called positive partial transpose, which includes separable operations and LOCC as a special case. But still, even under PPT operation, it's shown that discernible entanglement and entanglement costs are different. We have an explicit counterexample. And also more recently, one considers a very large class called non-entangling operations, which even includes like swap operation between A and B. So this does not produce entanglement from separable states. And of course, separable states cannot be implemented by local operation, classical operation. In this sense, it's a very large class, but still under non-entangling operation, these two are different. So in this sense, it's very challenging to formulate framework of entanglement theory that's equipped with irreversibility. We need a more non-trivial relaxation of operations to obtain a reversible framework of entanglement. So here's this motivates the problem of generalized constants lemma. So originally formulated by Branda and Plenio. So to obtain so the idea originally proposed by Branda and Plenio is to introduce axiomatically define a more relaxed set of operations tailored for asymptotic state conversion. So this should capture the essence of converting free states to free states only in the asymptotic sense. But still, and the spirit is similar to the axiomatic definition of adiabatic operations in thermodynamics. If you recall thermodynamics, thermodynamics works on adiabatic operations, but this is defined by what we cannot do in our world. So, for example, a quasi-static operation is not exactly performed within our physical lab, but still we appreciate the results, fundamental limits, and the quantitative analysis of thermodynamics. So, motivated by this, let's consider an axiomatic definition of operations that is defined not by what we can do in the lab, but by what we cannot do in the lab. In this way, the Branda and Plenio consider the axiomatically defined class of operations called asymptotically resource non-generating operations, which is a sequence of operations that generate no entanglement for any sequence of free states in terms of some entanglement measure called generalized robustness. Generalized robustness is a measure of resource in general. So in the original paper, this is a measure of entanglement. So this is defined as so we have a resource state and a set of free states, and choose some arbitrary state in the state space and consider some points, interpret these two, so that the point should be inside the free state, and then its ratio defines the generalized robustness. And this is a measure of resource in the sense that this does not increase under free operations. Yes.
So when you generally have an entangled state, if you add like a little bit of like whatever other state, will this will this cause a distillable entanglement like drop to zero?
Sorry, which part are you?
So will this generalized robustness
Yes.
agree with distillable entanglement?
No. This is a much larger quantity than distillable entanglement. So even if for example, this distillable entanglement is zero for bounded entangled state, but this can be positive for bounded entangled state. Yes. So what I'm saying is this is just a one particular choice of entangled measure in a sense that this is a mathematically defined function that does not increase under LOCC.
Can you show that generalized robustness is non-zero for all inseparable states?
This can be shown, yeah. This can be shown, yeah. So for any state outside of this, we can choose some state and then this is non-zero. Yeah, in this sense, this property is called faithfulness. So this is a faithful measure. But in order for this framework to work, we need to use this particular choice of resource measure in order for all the framework to work.
I think that generalized robustness is probably very hard to calculate.
For n qubit, this requires exponential runtime in general. Yeah, in terms of n. For dimension, it's polynomial. STP. There's a STP formation. Yeah. So, but okay, it also depends on characterization. If characterization of if f is separable state, this state itself is hard to characterize. Whether given state is separable or not is NP hard to decide. Then in this case, this itself is hard to compute. Yeah, but in the special case, the computation of this simplifies. But throughout this talk, what I'm interested in is a theoretical analysis. So yeah, many things are not computable, but we can somehow theoretically bound everything. Using this mathematically defined class of operations, it was so Branda-Perennial introduced several requirements for quantum resource theories. So in quantum resource theories are, as I introduced, quantum resource theories are defined by specifying set of free operations, but these conditions are required for the set of free states that is preserved by some certain choice of free operations. And Branda-Perennial introduced 5 conditions. That is, the set of free states should be finite dimensional closed convex, closed under tensor product, includes some full rank state, and closed under taking partial choice, and closed under permutation of subsystems when we consider n-fold subsystems. So under these mathematical conditions, the important point is that what they can show is that we can use regularized relative entropy of resource, which is a measure of general measure of resource, and this resource measure can be used as the entropy in the thermodynamics in a sense that this resource measure take a role that is analogous to entropy in thermodynamics. Regularized relative entropy resource is defined as the closest, given some state rho, consider n-fold of rho, and then take the closest free state, and then compute its relative entropy between these two, and then regularize it. And then this is a relative entropy. This serves, roughly speaking, this serves as a pseudo distance between two states. And then what Branda-Perennial has shown, okay, in its general sense, it's that so it's known that if so-called generalized quantum science lemma that I will explain in the next slide holds true, then we will have a second law in a sense that asymptotic conversion rate under asymptotically resource non-generating operation between any two states, ρ1 and ρ2, whose measure is non-zero, then this conversion rate is fully characterized by this single function. And then in this way, they formulate a universal framework with this regularized relative entropy of resource serving as a entropy in the second law of thermodynamics. And so this holds in a fairly general class of quantum resource theory, satisfying general assumptions. if generalized contention lemma hold true. So here's the setting. So I would like to explain the setting of generalized contention lemma. Generalized contention lemma characterizes the optimal performance in a certain hypothesis testing task. So this is a variant of hypothesis testing. So we are given some unknown state, and then we perform P of M, two outcome P of M measurement to distinguish between two cases. One is that the given state is an n-fold of some resource state, and the other case is that given state is a free state. So free state is also on the n-fold state spaces. And this is on the n-fold. So in this case, rho is the IID copies. But in the latter case, this free state can be highly, in general, non-IID form from some convex set of free states. And that the task is the hypothesis testing to distinguish between these two cases, whether the state is resourceful or whether the state is free. So in this hypothesis testing task, we have two different quantity, so two different types of measures. One is type 1 error, which is one is a type 1 error, and the other is type 2 error. So with these two outcome measurements, one represents that the given state is a rho, and the other measurement outcome shows that the given state is free state. But type 1 error shows that type 1 error means that even if a given state is rho, we mistakenly conclude that the given state is free. And we consider case that this type 1 error is upper bounded by some constant, by some non-zero, by some constant epsilon. Then we want to minimize type 2 error. So type 2 error is the error that the type 2 error is that the worst case error where the given state is a free state, but we mistakenly conclude that the given state would be the resourceful state rho. And as we increase n, we know that this type 2 error decays exponentially in n, and this R represents the decay rate, how fast this type 2 error decays as we increase n. And I will explain in the next slides. So yeah, so this R is not generalized robustness, but this is operationally defined quantity. And the question is, what's the optimal exponent R? And this is in general very hard to analyze because of the non-ID structure of the convex set of free states. So this was why this problem has been open for a while. So here's the original statement of generalized contention lemma. So generalized contention lemma characterizes this optimal quantity. So in this generalized contention lemma, so we assume that the set of free states satisfies the 5 assumptions that is made for in the same that is made for the framework of quantum theory. Then it says that for any type 1 error epsilon between 0 and 1, the optimal decay rate of the type 2 error is exactly given by the regularized relative entropy of resource. So in this sense, this optimal R is given by regularized relative entropy of resource. So this means that so this type 2 error decays like regularized relative entropy of resource. And in the special case where this set of free state is IID, then this lemma reduces to the conventional quantum science lemma, which shows that given two IID states, the optimal performance of distinguishing these two in terms of quantum hypothesis testing in the task of quantum hypothesis testing is characterized by relative entropy of quantum relative entropy between these two states. This provides the operational meaning of quantum relative entropy. And generalized contention lemma generalizes this lemma to non-ID case when the second argument is non-ID. So here's a small history of this lemma. So this result, this highly general result was originally announced by Branda and Prenio in 2008, and the full paper appeared 2 years later. They are published in CMP. This is a very huge paper, but more recently, some logical gap is found in a part of the paper, by Fan, Gore, and Wang. And then, but the part that had a logical gap was indeed based on the Branda and Prenio's paper. So based on this finding, so Berta, Branda, Gore, Lamy, Prenio, Regula, Tomichev pointed out a logical gap of the analysis of the original analysis of the general content Stein's lemma published in this paper. And then earlier, 2001, 2024, we also worked on providing alternative proof to provide we aimed at providing alternative proof using some continuity band of quantum relative entropy at that time shown by Bloom et al. But this part was, the band was unfortunately not tight enough. And then after uploading our paper, it was pointed out that this also had a logical gap. This was found by the author of this paper. And then so this problem is very hard to solve. Indeed, at that time, most of the works was focusing on avoiding the issue of using generalized content Stein's lemma by defining some more like unphysical class of operations that goes beyond the law of quantum mechanics, such as using post-selection or some non-positive probability distribution and so on, to formulate some operational framework of quantum resource theory with second law. But in this case, operations is not the proper subclass of GPDP map, but something with some unphysical assumptions. So here's our contribution. So in our recent results by this paper, we provide a proof of a stronger version of generalized quantum Stein's lemma, which includes the original statement as a special case. So our results shows that we assume a set of free states satisfying the first three conditions involving finite dimension, closed convex, closed under tensor product, and including full rank. And then we can show that for any epsilon between 0 and 1, the optimal type 2 error for epsilon type 1 error is exactly characterized by regularized relative entropy of resource. And our proof technique eliminates assumptions in the original paper because we developed completely different technique. And these assumptions are originally required for using the quantum definity theorem, which basically says that if you have a non-ID symmetric state, if we take partial trace of some part of it, it's very close to, if the original state is permutation symmetric, it will be very close to IID states. And then they try to use this result, but basically it's still unknown how to make this work. Yes.
Even if the set is close under permutation, the elements may not be permutation there. So why is this?
So we can prove that. We can prove that optimal state shown. If this row is IID state, optimal state in the set of free states can be chosen as permutation symmetric, and then they try to apply this. So this point is okay, but the bound is not tight enough. And also, soon after posting our work, Ludovic Lamy also proposed alternative proof of generalized content lemma. But this is for the previous version, imposing all 5 assumptions. And our result is stronger in the sense that we eliminate some of these assumptions. In our paper, we also prove we also use these results to provide a generalization of the formulation of second law. So we show that under asymmetrical free operations, we have second law not only for resource theory for states, but also resource theory of channels called dynamical resources. In the sense that for any asymptotic channel conversion under asymptotic free operations, this conversion rate is fully characterized by a single function. That is, I will define in the later part of this talk. So yes. But yeah, so we show the analogous results for any classical quantum channels, which I will explain in the later part of this talk. In this way, we open the way to formalize and utilize a more generally applicable framework of second law by proving generalized quantum Stein lemma and its stronger version.
I'm sorry, but
yes.
Can you show the definition of beta epsilon again?
Beta is so this is type 1 error. So we misidentify this one with this. And beta is misidentify this one with this in the worst case. So we limit this within epsilon and then consider minimizing the other one. So that's a hypothesis thing. Yeah. So so maybe it's So we will briefly discuss how to prove generalized computational lemma, since this is a main part of the technical contribution. So what they are showing is that, so assuming these three conditions, for any epsilon between 0 and 1, optimal type 2 error is exactly characterized by regularized relative entropy of resource. And the actual proof is composed of two parts. One is a strong converse part, meaning optimality. The other is the direct part, showing achievability. This means that optimal type 2 error cannot be larger than the regularized relative entropy resource. That's the optimality part. And the achievability is that any, we can actually find we can actually achieve type 2 error that is larger than this regularized relative entropy resource. So, while I write limit here, our technical point is that the existence of limit is not a priori obvious, but on the right-hand side, this quantity is subadditive. So we can prove that this regularized relative entropy resource has a limit. So, and then we bound lim sup and lim inf of the left-hand side. So the existence of limit is not pretty obvious. But from this upper and lower bounds, we can also see that this limit exists and then exactly coincide with the well-defined limit on the right-hand side. So before going into explaining upper and lower bounds, this is important. I'll use one slide to introduce important technique. This is a characterization of this quantity by using min-max theorem. So the type 2 error is a worst case. So in the generalized confidence lemma, we minimize a worst case type 2 error defined like this. So this is we want to distinguish these two states in the worst case. But a different quantity is that in a different setting, we could also minimize type 2 error for each state in this sequence, and then take the take the maximum between among these choices. So this is this quantity represents this. So for each choice of this, we distinguish these two, and then later we consider maximization of this beta among this choice. And these are different in a sense that min and max are switched. In the most general case, minimax, we have a minimax inequality showing that this quantity here is lower bounded by the quantity here for any set of f. But when f is convex and compact, we can show that these just indeed coincide. So this is called minimax theorem. And this simplifies our analysis a lot. So it will suffice to analyze the maximum of the right-hand side quantity. So max min, so we analyze the quantity with max and min in this order instead of the original quantity, but still these two coincide. So using this, we give a simple proof of strong converse the strong converse part it has been proved validly by the original Brandon Plenio paper, but their argument required additional assumptions that our proof does not require. So I would like to provide a simple proof, explain about this simple proof. So the goal is to show that the lim soup of the left-hand side is upbounded by the regularized relative entropy resource. To do this, we take some optimal m-fold non-ideal state that minimizes this relative entropy on the right-hand side. And we want to bound the left-hand side by using this quantity. But the left-hand side is in general very hard to analyze. So this is like n-fold state, and it's a limit. And also this and also this beta is an operational quantity. So in general, this is very hard to analyze. So to analyze this, so we need to bound betas by some additive quantity, some additive mathematical function. And to do this, so we use n-folds of free states that is chosen here. And then we take some very small reminder state to form some n-fold free state. And then in the end, we can, and then at the core part of our proof, so we start with this left-hand side and then convert, and then take some, so for this max, we take some particular state, and then we basically form some additive upper bound to bound this operational quantity using some mathematical additive quantity, and then take the limit to show that this is bounded by some relative entropy. To do this, we show a simple derivation using some additive upper bound formed by a function called linear relative entropy. And so in this way, we bound this operational quantity by mathematical function. Yes.
Could you explain the first inequality one more time? Because like on the left-hand side, you are maximizing over all low free.
Yes, yeah. So this is maximum. So but here is a minus here. Everything is log. I skipped so it's a maximum.
But in the middle, you have row tilde free, which is that's not a state in.
So yes. So this is a maximum, and then I chose a particular state. So this is since this is minus, so this max is a smaller.
Oh, okay.
Yeah. So yeah. We just chose a special choice and then applied. So this special choice is required because to use additive upper bound.
Let me ask about the small n.
Yes.
The first one, small n is the finite, okay, fixed, and then now the started, and then n goes to infinity.
Yes.
This is the point.
M. So yeah, we fix M and then we obtain this. For each n, we obtain this bound.
Now ask about low bound, that upper bound.
Upper bound, yes.
Okay. Low bound, then n is now the started, the small n is fixed, and then small n goes to the infinity. Okay, now set up the lower bound. Is it start point?
Start.
The starting point for your default. You are talking about the upper bound. Now I ask you about the low bound.
Low bound will be explained in the next slides since it's more complicated. Yeah, so I'll explain about the lower bound in the next slides. Yes, so now that we have a upper bound, the upper bound is given by regularized relative entropy resource. The next step is a more non-trivial part of lower bounds. So for the lower bound, lim inf of this operational quantity should be lower bounded by regularized relative entropy resource. And we want to show this. But here's the challenge here is that the challenge here is that so this part is more complicated because we need to so we need to really analyze the achievability. So and indeed the original analysis also has some error. So we cannot rely on the existing technique to prove this essentially. So to prove this, we fix some optimal sequence in maximizing beta. So we have this optimal sequence. And suppose, and if this holds, so the regularized relative entropy resource can be smaller. But suppose that we have a suboptimal sequence that turns out that is let's take some suboptimal sequence that's larger than this. And then that is, so that does not satisfy this. So if the right hand side is smaller, we can we already have proof. But suppose that we initially have some sequence, suboptimal sequence that does not satisfy our goal. Then the key strategy is that for any epsilon, so we can show that we can update this suboptimal choice of sequence by using this optimal state beta and the suboptimal choice of free state, and then by mixing some free state. So we mix these three and update this suboptimal sequence into more optimal one. But we can show that then this difference between this D and the optimal sequence on the left-hand side, optimal quantity on the left-hand side, can be reduced by updating this sequence. So every time we apply this update, this suboptimality can be reduced by some factor smaller than 1. And by repeating this k times, we can arbitrarily suppress this suboptimality so that this in the end goes to 0. So we can show that these two can be so we can, after the infinite times update, we can show that this indeed the right hand side can be indeed small. So this is a key lemma that we show that we have shown. In this way, we identify how to construct the optimal sequence, minimizing the relative entropy, from that maximizing the operational quantity beta.
Okay, let me ask you about, I try
Yes.
to understand your point.
Yes.
Okay, your key member are the low n free, n is the fixed. Okay, start with the n and the
Yes.
small n is fixed. And then also while then maximize the beta. Okay, beta is a fixed. Also,
N is not fixed. We always take.
I understand that,
Yeah.
but before that, I asked you about, assumption, you have the small n,
Uh-huh.
as the fixed, and the y also the, beta is also fixed on the maximized. So we have the two parameters, small n and the beta, okay?
Small n and
Beta,
beta.
right.
Beta, yes, beta, yes, yeah.
That's 1/T is the temperature, right?
Yes.
Right, if the temperature is in 0, what happens, I ask you about, and fix it.
Okay, beta is not temperature, but type 2 error. But yes, yeah.
Right, and then for example, beta is for example, maximized, that means temperature is 0.
Uh-huh.
And then, now you fix it, the small n, and then fix it, okay? And then that fix means finite.
So maybe, yeah.
Both the temperature and both the second line, the bottom of the second line, you have the and goes the small n goes to infinity for maintaining the original temperature at the 0 or something.
Beta
So-
is not a temperature.
Beta is not temperature. So I will explain this in more detail after the talk. Maybe that'll be better. So yeah. So my point is beta is not temperature. So there might be some. Yeah. So yeah, beta is type 2 error in hypothesis testing.
This I think that is the phenomenon and probably for example type 2, right? Is similar to this.
I think we should, maybe we should do this afterwards, yeah.
Yeah. So that type 2 error this type 2 is a convention in hypothesis testing, nothing to do with Feynman algebra and so on. So I will talk later about this. Yeah. So the most non-trivial point at this point is how to prove this update bounds. So this point is the most technical part that was not able to be achieved in the previous work. And I mean, So, I mean, this idea itself does not appear in the previous work, but the most technical part is how to prove these update bounds. So there are two techniques involved. One is a pinching, and the other is an information spectral method. In this slide, I will talk about pinching. In the next slide, I will talk about the information spectral method. By combining these two, we can prove this. So the pinching is a technique to make non-commuting operators commute. One difficult point of analyzing this quantity is that these two operators in general does not commute. So this makes the analysis hard. But we use a technique of pinching to convert these two operators into another operators that commute each other. So to do this, we start with these updated states. And then, so this state itself is defined on the n different subsystems. So it has exponentially many different eigenvalues in terms of n. So it has exponentially many different eigenvalues. But we round these eigenvalues in such a way that we only have a polynomial number of different eigenvalues by rounding these eigenvalues appropriately. So this, of course, we will obtain a different state from this, but we mathematically manipulate the eigenvalue so that we only have a polynomially many different eigenspaces for different eigenvalues. Then for each polynomial number of eigenspace, we define this projector, and the pinching map is defined as a project dephasing in terms of this projection. Important point is that there are only polynomial number of projections after this rounding up eigenvalues. Then what we can show is that this manipulation of rounding eigenvalues and performing pinching makes these two mutually non-commutative operators commute to each other. But with these manipulations, one can show that this relative entropy, the asymptotic, so regularized value of relative entropy does not change. So we can show this. So this is a particular property of relative entropy, quantum relative entropy. So if you recall the previous work relied on continuity bounds that manipulate this state in the second argument, and then approximate this state by trace distance, and then try to use some continuity bound on the second argument of relative entropy. But in this case, this relative entropy is disturbed too much. And then, especially, we tried to do this approach, take this approach, but we indeed failed because such continuity bound does not scale very well. By contrast, this pinching looks very different from such a continuity bound-based approach. But indeed, one can show that this does not disturb D in a sense, in the asymptotic sense. Then while we can make the operators commute, so we have an updated goal. So we have a mutually commuting operators, relative entropy, and then we need to bound this we need to bound this quantity from above. So this is a final. Then to bound this quantity, relative entropy with some mutually commuting operators, we use a technique called information spectral method, which is a technique to convert this operational quantity beta into the probability of finding the state in the typical subspaces. So this is a technique to convert beta into some probability. So, and then basically, by combining these two, the relative entropy between mutual commuting operators can be, so this is by definition. And then we can can decompose this part into three parts, three subspaces, using this information spectrum method. And then each of these terms can be bounded. And in the limit, we can show that this converges to some desired bound. So that's a rough sketch of the proof technique. So in summary, so we used two different techniques, pinching and information spectrum method, to complete to provide new bounds on quantum hypothesis testing. So once we have proved general constants lemma, so we also talk about its application to quantum resource theories for dynamical resources. So Brandon-Prenio shows Brandon-Prenio originally for entanglement theory and also later work showed that if generalized constants lemma holds true, we will have a second law for the quantum resource theory for states, meaning that asymptotic conversion rate between two states under asymptotically resource non-generating operation is fully characterized by regularized relative entropy resource. So these are properties of quantum states, and this is in the quantum resource theory called static resources. But the applications of quantum resource theories is nowadays even broader. One can also consider dynamical resources given in the channels for the communication, and this has application in analyzing communication scenarios. But the challenge here is that in general, quantum channels are much harder to analyze compared to resources for quantum states due to the existence of unknown inputs. Yes.
Maybe I missed a certain logical part, but well, I think what you proved is about certification test.
Yes.
Fidelity or error is bounded by this relative entropy.
Yes.
How does that convert to the state conversion?
I will, in the end, this will turn, yeah, I will explain 2 or 3 slides. Okay. Yes, yeah, so this state conversion can be constructed using this state discrimination task. Yeah. So to avoid the difficulty in analyzing the fully general quantum channels, we worked on so-called classical quantum channels, or CQ channels for short. This is a class of channel where input is classical, and then it outputs quantum states. We worked on this to avoid hardness of analyzing general channels with quantum inputs, but still this includes quantum resource existing formulations of quantum resource theories for states as a special case when input dimensions are 1. So the framework is as follows. So the free operations is a subset of operations that converts CQ state into CQ states. This is called, this is a channel converts, operation converting channels into channels. This is called super channel. And the set of free CQ channels is free CQ channels obtained by any non-resourceful CQ channels by free operations. And anything non-free is resourceful. And the conversion rate is defined just in the same way as state case, where the approximation in the state conversion is now measured by the trace distance between choice states of the channel. Then in the same way as, just in the same spirit as state case, we can define asymptotically free operations that has 2 conditions. One is the same as the state case. This is a asymptotically resource non-generating property. It does not generate a resource in terms of some resource measure defined in an analogous way as global generalized robustness. But for the channel case, we needed to impose another condition on its asymptotic continuity. So if the two input channels are close, then after the conversion, the resulting output channels should also be close. We need to impose this condition for our set of super channels. In the case of QRT for states, this is automatically satisfied. But in the case of channel, we need to impose this. Then in this way, we identify the appropriate class of superchannels for which for which we will show that second law of quantum resource theory holds. So here's the result. Assuming that the set of free CQ channels satisfies the same assumption as the state case, then we can show that conversion between two CQ channels, asymptotic conversion rate between two CQ channels under asymptotically free operations is fully characterized by regularized relative entropy of resource defined for CQ channels, just in the same as quantum state case. And in this way, we show that we can use some generalization of regularized relative entropy of resource to CQ channels as a entropy that characterizes state convertibility in thermodynamics. To prove this, to prove this result, our proof is composing the two parts. One is achievability, the other is optimality. So in the following, I would like to briefly discuss how to prove these two parts. So the direct parts indeed requires generalized computational lemma. For the direct parts, the key lemma is a proof of the relation between generalized relative entropy of resource and the robustness measures. So this was originally proved for quantum resources on states, and this can be seen as a special case of a result with one-dimensional inputs. But our proof is more general than the previous result in a sense that previous result does not guarantee the existence of this mean and lim, but we show that this probably exists. And then using this characterization, we explicitly construct an asymptotically free operations, achieving this optimal rate. And this looks like this. So this looks like, so to construct this, we use this state discrimination task. So given some CQ channel, we input some maximal entangled state to form some choice state. And then we perform P of EM to distinguish whether it's resourceful or free. If it's free, we perform one of the channels, and if it's resourceful, we perform the other channels. And then we can show that if the resource state if the given channel is resourceful, this achieves the desired conversion at the optimal conversion rate. If this is free, then the resulting state also has a very small regularized robustness. So we can prove this. So this is defined in a very axiomatic way. So in the lab, it may be very hard to implement if you're only restricted to free operations, like physically motivated free operations. This may be very hard to implement. But still, if you recall
thermodynamics,
so adiabatic operations are also axiomatically defined. So this is in the same spirit. So this certainly satisfies the axioms. So in this way, we explicitly construct superchannels for optimal dynamical resource convergence for CQ channels. For the optimality, so conventionally, in the conventional resource theory, asymptotic conversion rate is upper bounded by relative entropy of resource. But in our case, it's not straightforward to directly apply this because we are working not on free states, but what we are using is asymptotically free states that slightly generate entanglement before taking asymptotic limit. So we cannot directly apply this. But we have proven an asymptotic version of monotonicity of this function. And then in this way, this function satisfies our desired property of asymptotic version of resource, the monotonicity of the resource measure. And then by combining the our requirement of asymptotic continuity, we can prove the optimality using these two parts, these two facts here. So this is a rough sketch of the our result. So I would like to briefly mention the outlook of what we can take from this development. So this result is so the implications of generalized content lemma is indeed very general. So it has implications for quantum resource convertibility in many scenarios. One interesting thing would be constant overhead magic set distillation. So we recently showed that under stabilized operations, the conversion rate in magic state distillation can be positive. But in general, under stabilized operations, this optimal conversion rate is very hard to characterize. But if we work on axiomatic approach by defining some asymptotically magic non-generating operations, then we can indeed exactly characterize optimal conversion rate from any noisy state into a magic state. So in this way, so we have a rare example of fully characterizing the optimal conversion rate.
Here, then we define three states as those that can be only generated by product state and then Clifford. That's definition of three operations.
Stabilized operations are defined like that. Yes. Stabilized operations are the set of operations composed of Pauli eigenstate preparation, Clifford gates, and Pauli basis measurements. But asymptotically resource non-generating operation is much more like, it's very hard to characterize. So it's a mathematically defined one. Okay, I have more details in the next slides. So other applications includes various bounds in quantum information theory. For example, faithfulness of regularized relative entropy of entanglement and squashed entanglement has been initially proved by using generalized content lemma. Now we know alternative proofs of these facts, but I'm sure there will be many other interesting examples in quantum information theory. And this Stein's lemma can be used as theoretical tools to tackle difficult problems. And also we are working on axiomatic extension of our axiomatic framework further. So if you're interested, I'm very happy to discuss. So in this way, proving generalized Stein's lemma, in my view, is not the end of solving big open problem, but the first step of its vast applications. So to be more specific, so we recently analyzed constant overhead magic set distillation. And magic set distillation is conventionally analyzed in a bottom-up approach. So people are interested in a class of operations motivated by FTQC. This is stabilized operations. This is composed of preparation of zero state, Clifford gates, and Pauli basis measurement. Then our recent results in a different paper show that asymptotic conversion rate from noisy input state to pure magic state can be non-zero. So asymptotically, this rate can be non-vanishing. So in this sense, it's a constant overhead. So this is the terminology in FTQC. But it's very hard to characterize this optimal rate under this physically motivated class of operations. By contrast, if we take top-down approach, we can define asymptotically resource non-generating operations, and then we exactly characterize this conversion rate as using the ratio of regularized relative entropy of magic. So in this sense, these two results are complementary to each other. Still, the open problem is what's the optimal rate of magic state distillation under this physically motivated stabilizer operations. So if you're interested, I'm very happy to discuss.
Can you calculate this right-hand side, the ratio? Like, is there a simple way to calculate this arrangement?
In general, no. In general, no.
In simple cases, do you show that calculation in your paper, or is it just theoretical?
It's a theoretical value since this requires this requires regularization. So in general, you may be able to have some bounds, but further research is needed to obtain tight bounds or interesting non-trivial examples for this calculation. Yeah, so it would be a very interesting problem to investigate further.
People try to define a magicness in a given state. Do you think that term of the right-hand side can potentially become a most general notion of maybe magicness in a given state?
There are many ways to define magic measures, and it returns, given some mixed state or pure state, it returns some number. But the important thing is what this number means, in my opinion. So in this sense, this is a rare example of magic measures that has an operational meaning exactly in terms of conversion rate. So, but if we need to, if we want to prove such a good theoretical result, we might need to, compromise computability. So there's a trade-off, I think. I'm not sure if it's inherent or not, but such trade-off often exists in quantum resource theories. So in conclusion, we prove general consensus lemma with much smaller assumptions than previous work. And this implies second law of quantum resource theories holds not only for states, but also a fundamental class of classical quantum channels. In this way, the universal axiomatic framework for quantum resources is now available. And much like thermodynamics, driving has driven our technological advances ever since Industrial Revolution. So now is an exciting time to take a look at this further. Thank you very much for your attention. Yes.
This one. Yeah, so say I have like a single qubit state.
Yes.
And let's say it has some that, let's say, it's definitely not a stable state or something. Could it still be that this quantity is
Zero.
I mean, let's say I have a single qubit state.
Yes.
It's not a state quantum state.
Yes.
Like, if that's non-zero, is this quantity always non-zero?
For single copy.
Constant number of qubits. I guess the reason why I'm asking this question is because even if it has magic, if it's too noisy, they may not be able to distill any magic state.
Are you asking faithfulness maybe? So if this state is not stabilizer state, can we guarantee that this is always non-zero or not? This has been shown for entanglement, but for magic, I haven't read any proof. Maybe it can be shown, but I need to check.
And if my question is, could you say a little bit more about the thing about the two conditional assumptions that you have elucidated?
Two additional.
In the living proof work, he also did pinching, and at that point he used some permutation geometry structure, right? So can you explicitly say in which part that you can eliminate these two additional assumptions?
So Ludovico's work, when we wrote a proof, Ludovico's work was not there, so we don't know how Ludovico used that. But in the original Fernand Brandao and Martin Polenio's work, they considered that. So they considered optimizing relative and so yeah, they worked on bounding these quantities. So since this is so the challenge arises when this is non-ID. So if it's non-ID, so this is non-ID state. But if this is IID, we can we can restrict this minimization to the set of symmetric state over permutations of these n subsystems. Still, this minimization is achieved. So this can be chosen to be permutation symmetric. But still, this is a permutation symmetric non-ID state. But if we take like square root n of subsystems, and then, if we trace out square root n of sublinear number of subsystems, then by tracing out small subsystems of permutation symmetric state, the state is becomes close to IID state in terms of trace distance. Then, so this is called definite theorem. And then the original attempt is to use such statement to reduce this non-ID problem to IID problem. But since due to the small error appearing in partial trace, it's indeed very hard to analyze because the continuity bounds on the second argument is very subtle. It's not so tight, and then there are many counterexamples. Yeah.
Compared to there, so you did the direct typical space.
Yes, yeah. Yes. So basically, what we need to learn from the previous work is that we cannot take partial trace, and we cannot use continuity bound. So if any proof technique that try to go through this will fail. So okay, we don't know how to still fix the original strategy. So we need to use really like what we allowed is a pinching, and also yeah, so pinching is allowed. Yeah, so yes, that's yeah, it's a different technique.
Bring this idea to you have the in your procedure it's zero epsilon 2. Could you say what specify the epsilon 0 error is epsilon 2? Could you make the next slide?
So this.
Yeah, here. Could you say more about the procedure on this epsilon 0 and epsilon 2?
Zero.
Yeah, epsilon 0 error. Look at this kind of Could you say more?
This one. Okay. So this is like so information spectral method is a method to convert bounds on beta into bounds on probability, and this epsilon in the beta appears like here. Epsilon here appears like here, and then by setting. Okay, this does not include some. Yeah. So take some parameter, take some small parameter, epsilon 1, 2, and 3, and then we can take, and then from the bounds on beta. So these are parameters that we choose to be the small parameter that we choose, and then we decompose. So yes.
Okay, and then now the epsilon 0, where's the, how do you, okay, what does it mean the epsilon 0 in this situation? Do we have to remove the this epsilon 0?
Yes, yeah. So these are small parameters that we arbitrarily choose, and then in the end, we take limit of it's we take it vanishingly small. Yes, yeah. So these are parameters that we choose arbitrarily. Yes.
Thank you.
All right, so let's thank Hayata for very much.
Very much.